Okay, welcome everyone. Today is the second lecture of the lecture series on quantum mechanics, and in today's lecture we are going to discuss about the Schrodinger equation. All of you must have read this about this equation in your masters or in your graduation courses as well. So what Schrodinger equation is? It basically predicts the behavior of a dynamic system. So in Schrodinger equation, we discuss about different operators and we try to predict various variables such as energy and position of a particle. As we all know that Schrodinger equation can be time dependent or independent, and in this scenario we are going to discuss both cases and we will try to solve the Schrodinger equation. So consider a particle of mass m which is moving along x-axis in the potential field Vx, and we can write total energy of system. From the law of the conservation of energy, we know that H psi is equals to E psi, where H is the Hamiltonian of the function, and we can write Hamiltonian as the sum of potential energy and kinetic energy, as potential energy for EP and kinetic energy EK is equals to E psi. We are going to derive the Schrodinger equation from these two values, as we discussed in yesterday's lecture that we are going to discuss about the potential energy and kinetic energy. As we know, kinetic energy, as we know that kinetic energy Ek can also be written as P square divided by 2m, where P is momentum. And in yesterday's lecture, I've shared you a PDF on operators, and from that lecture, we can understand the value of momentum operator, where P is our momentum operator, which is equals to iota h bar del by del x. And we are going to replace this value over here for kinetic energy, and potential energy, which is Vx, is already given. So we are going to put both these values in this particular equation. So we have kinetic energy, which is iota h bar divided by 2m, iota h bar the square, because here we are having momentum operator square, into del square over del x square plus potential energy, which is Vx. Vx is equals to E, and here all this function, so this all function E Vx into psi is equals to E psi. And from yesterday's lecture, we also know that value of E is equals to iota h bar del upon del t. So again, we are going to replace this value over here, and we will get iota h bar del psi upon del t. So in this particular equation, we can observe that here psi is derivated with respect to t, and here we are going to have the double derivative of the function psi. So our psi, which is a function of position and time, can be written as capital X, which is a function of x, and capital T, which is a function of time. We are just trying to have some values of psi so that we can put over there. So after putting these values in this equation, so here what we have, iota h bar square divided by 2m. So iota square minus 1, h bar square divided by 2m, h bar square divided by 2m. Now we need double derivative with respect to x. As we know, one part of this function depends upon x, whereas other depends on t. So t will be the out of that derivative. So here it's t, which is a function of time, and we are taking this derivative with respect to position, del square capital X upon del x square. Okay, so now Vx, we are putting the value of psi x and opening this bracket. Okay, so Vx into capital X capital T is equals to iota h bar, x will be the out of derivative because we are taking derivative with respect to time. So here we will be having del t capital T over del small t. So this is our equation which we need to solve. Number it as equation 1. Okay, so now what we are going to do, we are going to take xt into t common from both sides and we are going to cancel it. So when we are taking xt into t common from this bracket, we will be having capital X into t. Here we are having h bar square over 2m. So as we are having xt, so here we will be having x in denominator, del square capital X upon del small x square plus v of x. So this thing is common from both the terms, which is equals to capital X capital T iota h bar 1 upon capital T del capital T upon del T. And now both of these things are cancelled and this is our final equation. So what we need to observe in this equation is that this is the function of x only, whereas this is the function of time. Sorry for writing. So this is the function of time. So we need to solve that part. So what we are having here is iota h bar 1 upon capital T del capital T upon del T is equals to our energy. Okay, so here E is the energy. So we are going to rearrange this equation in order to find the value of energy in terms of time. So this is going to be del capital T upon T is equals to 1 over iota h bar E into dt. So what will be the next step? Can you guess? Okay, it's going to integrate the equation. So we need to integrate the equation. So when we are integrating this equation, so what we will have, natural log of t, obviously, sorry, I'll add one more step over here so that you can understand it well. So del capital T over T integration is equals to, so we are taking multiplying both sides by iota. So here iota square minus 1. So it's going to be minus iota over h bar integration E dt. So this is our equation. So let's do it, complete it over here. I'm just not trying to raise many equations so that you can understand it well. So here it is natural log of t, and this is going to minus is equals to minus iota over h bar E as a function of t. So this is going to be t is equals to some constant. We were just trying to add some constant times exponential e raised to power minus iota h bar E t. So that particular equation is the time dependent part of Schrodinger equation. Let's just write it over here. T is equals to e raised to power minus iota over h bar into et, where t is the time and E is the energy eigenstate in which particle is present. So we are having two. Now let's deal with this part of the equation. As we have discussed this part, time dependent part, now we are going to discuss the time independent part. Please try to solve this equation independently, because we are going to need this equation so many times during our course of quantum mechanics. So here h bar square over 2m 1 over x del square x over dx square plus v of x is equals to E. Now taking this x common from both sides from the equation, I mean, so this is h bar square over 2m del square capital X over del x square plus v of x into x, and thing we took common 1 upon x into x is equals to E. Okay, so what we are going to do is we are going to multiply this term into that particular region, I mean energy value, so minus h bar square over 2m plus into del square x upon del x square plus v as a function of x minus, we took E this time, multiply this thing over there. So this is E capital X as a function of x equal to 0. So further what we are going to have as a final equation is h square h bar square over 2m in del square x over del x square plus Vx minus E into x is equals to 0. This is the equation for your time independent part. So we are having two equations, time independent Schrodinger wave equation and time dependent. So these two equations we are going to use in future in order to find the energy of particle. That can be either in infinite potential well, that can be in your harmonic oscillator, and so many other quantum mechanical problems. So try to remember the value of this particular part, because we are going to put this value directly in our numericals. So everyone, I guess this is enough for today, because we need to keep these things in our mind, how to calculate the solutions of Schrodinger equation in numerical problems. So let's just write the time dependent part again. So for time dependent, our equation is T is equals to C e raised to power minus iota over h bar e t. Okay, and this is our time independent Schrodinger equation. So that's all for today class, and tomorrow we are going to discuss the numerical related to this particular topic. I hope you understand this very well. Thank you.